This is Al-Hussein Abdelmonam Al-Shafai. I will be presenting some techniques to accelerate the online training of fully connected layers on hardware. This work is a part of our publication, an efficient hardware implementation of CNN-based object trackers for real-time applications, which was published in Springer Neural Computing and Applications Journal. We focus on the hardware implementation of the online training of the fully connected layers in deep neural networks. We addressed the transposed reading issue, the latency of the external memory, weight updates, and how to store features and weights in the external memory. We have three fully connected layers, starting from X4, the output from the convolutional layers. In the forward path, we obtain X5, X6, X7, and then in the backward path, we obtain from the loss the back-propagated errors and the delta weights. In this step, we need the transposed form of W6 and X6, and here we can get the new weights of fully connected 6. Same thing for fully connected 5. We need the transpose reading of W5 and X5, and then the new W4. In this example, we have 8 matrix multiplications as shown in the yellow rectangulars, and we need also the transposed operations. The transposed reading required in the backward path is time consuming. It requires 4x more memory accesses than those required in the forward path. So in our proposed implementation is that we took the transposed operator to both sides of the equation. So we obtain the loss in the transposed fashion, and we calculate the propagated errors and the delta weights in a transposed form. In this implementation, we get rid of the transposed reading, and we need only to store the loss in transposed form and the weights, delta weights. But we will show that the update of the weights can be done on the fly, and this will not consume more extra cycles to access the memory. So next is how we address the latency of the external memory. So if we have one memory to store the weights and another memory to store the features, previous works focused on reducing the number of external memory accesses, in addition to compression techniques. These are suboptimal solutions. They don't consider the memory latency per cycle. Therefore, we focus on reducing the external memory latency via data arrangement and how or the order of reading and writing. So if we have this matrix, instead of storing matrix row by row or column by column, we store chunks of each row and start by the first row. Just store a chunk. The width of the chunk is the maximum width that we can read from the memory. In this example, 512 bits. So store the first chunk of the first row, then the second row, and third row, and so forth. If we manage to read the matrix in this order, this should yield the minimum latency. And then, in order to perform matrix multiplication, we always have mat1, mat2. So for mat1, we start by reading a sub-matrix 8 by 32 and store this sub-matrix on the chip, and then start to read the first chunk of mat2 and do the matrix multiplication, or do this multiplication first column of submatrix 1 and the first chunk of matrix 2. This will be 256 multiplications. So if we have 256 multiplier in hardware, this can be done in one clock cycle. Second clock cycle, also we can read the second chunk of mat2, and we have the second column stored in a chip. This multiplication as well can be done in one clock cycle. And then we can obtain the partial sums of all these submission and store them in a chip. No need to write back the partial sums to the external memory. So at the end, we will obtain the result, the submatrix in the result, which will be also 8 by 32. In order to achieve this, the order of reading matrix 1 will be as follows. We start by reading the submatrix 8 by 32. So this should yield the minimum latency because we read sequentially. And then we will continue in this order. For matrix 2, we read also sequentially the chunks, which is 32 element, and we will continue in this order. So also this should yield the minimum latency from the external memory. For the result will be treated as mat1 or mat2 in the following steps in the training of the fully connected layers. So we write the result in the same way that we need to read them. So we write the result same way how we read matrix 1. Next is the weight updates. We don't write back the delta weights to the memory. If we do so, we have to read the old weights and delta weights again and write back the new weights. Instead, we read the old weights and do the matrix transpose on the fly. As we said, we calculate the delta weights in a transposed form, 8 by 32. So we don't write this chunk or this submatrix to the memory. We read the old weights in 32 by 8 chunks or elements and do the update on the fly and write back the new weights, which will be 32 by 8. So for the memory allocations, we start by X4 and the 3 fully connected weights. We avoid reading mat1 or mat2 from the same memory. So here we write X5, X6. For the loss, we write it in transposed form. Loss will be required as mat1 to get the weights and mat2 to get the propagated errors. So that's why we write the loss in both memories. And same thing for DX6, the backpropagated error. It will be needed as mat1 and mat2. And then update the weights. Update W5 and then update W4. So as a comparison with a recent work, we achieved 44 frame per second compared to 16.2 frame per second. We didn't use approximation in the backward path. We use a normal back propagation and still achieving same or comparable performance results for the object tracker while achieving 44 frame per second. Thank you.